Welcome to the presentation. By the title of the presentation, and especially the graphics shown, we might be thinking that there's no contest. If our main goal is to reach a point very fast, then the option is obvious, the left one. But there are other parameters to consider. For example, how much it's going to cost us to get there. In the context of computer vision, the authors on that paper asked the question if it is still necessary to use more traditional techniques because of the advancements in deep learning. And this is what they found. Yes, there is still a need for traditional computer vision techniques in the era of deep learning. While deep learning has pushed the boundaries of what was possible in digital image processing, it doesn't mean that traditional computer vision techniques have become obsolete. There are some problems where traditional techniques with global features are a better solution. The advent of deep learning may open many doors to do something with traditional techniques to overcome the many challenges deep learning brings, such as computer power, time, accuracy, characteristics and quantity of inputs, and others. Something to note is that the paper was written in 2019, that by the fast pace of changes in today's world seems like a long time ago. The world has changed fast. What might be next? This newer article retraces the brief history of computers and artificial intelligence to see what we can expect for the future. It highlights how rapidly the world has changed due to advancements in computer technology and artificial intelligence. The article also discusses the evolution of AI systems, from the Theseus, a remote control mouse that could find its way out of a labyrinth built by Cloud Shannon in 1950, to modern AI systems that have language and image recognition capabilities, surpassing human levels. It also emphasized that despite their brief history, computers and AI have fundamentally changed what we see, what we know, and what we do. Besides mentioning the training computation that was used to train AI systems, they also mention a number of tests in which human and AI performance were evaluated in 5 different domains. Details of those tests can be found in this paper. The benchmarking is done by an open source platform called Dynabench. The platform encourages a human and model-in-the-loop approach to dataset creation, where annotators aim to create examples that a target model will misclassify, but another person will not. The creators of Dynabench argue that it addresses a critical need in the NLP community. The initial performance of the AI system is set to -100, and human performance in this test is used as a baseline that is set to 0. This means that when the model performance crosses the 0 line is when the AI system scores more points in the relevant test than the humans who did the same test. For systems that recognize handwriting, we can see that the evaluation starts just before 2000 and how rapidly that curve reaches the 0 line, which indicates that the AI system has performed better than humans. For speech recognition systems, we can see that the slope of that curve doesn't go as fast as in the previous application. Speech recognition has been a topic of research for a while. In a 1996 international conference, it was mentioned that that would be the decade where speech recognition will be achieved. If we allow ourselves to use a time machine and go further 10 years, we can see that it is until 2016 when we can achieve results better than humans. For image recognition, we can see that the pace of improvement was considerably faster than the other 2 applications. For reading comprehension, we can see how fast AI systems perform better than humans. For language understanding, quite mind-blowing. Is there a chance then for traditional computer vision methods to compete with deep learning approaches? Let's consider segmenting eggs as shown in that video in real time, using both techniques. Using deep learning methods, one can try YOLO to track the eggs and define areas to be used with metasum. For computer vision, an approach can be enhance the image followed by thresholding. Let's elaborate on how the computer vision technique works. For this, we will think that the image is in a three-dimensional space where the height corresponds to the intensity of the pixel. For image enhancement, we will be using morphological operations. If we were to apply morphological closing, we use an spherical structuring element and think of that structuring element rolling on top of the image, as it is shown there. For morphological closing, the sphere is being rolled underneath and pushed upwards. The size of the structuring element will not allow it to push further than those two lines corresponding to the metal rods in the conveyor belt. As the structuring element rolls below the areas where the eggs are, it will be pushed upwards. The enhanced grade level value image will consist on the position of the center of the sphere, so as it rolls underneath, we can see the results for that particular size of the structuring element. We can see how in areas like that, the structuring element will not fit and reduce the intensity of those pixels. Using different structuring element sizes, we obtain several images that when we average them, we obtain that result. Using that image and multiplying it by the original one, we can see that the net effect will be to reduce the intensity of the background only, not the X. A simple threshold can then be used on the image on the left and obtain the segmentation that you can see in the image on the right. The result using both techniques is shown in the video. As we can see, the segmentation of the X is successful for both, but one can argue that computer vision approach on the left give us more time to extract information such as the orientation of the X, indicated by the arrows. This faster implementation may allow us to decide between a GPU or a CPU, in which not only the cost is important, but maybe also the power consumption. This offers us a flexibility of options to offer our client and let them decide the final solution. Engineering solutions not only involve price or power consumption. For example, let's consider self-driving cars. Cameras can be added to the car so that together with artificial intelligence we can drive in beautiful roads automatically. Bad weather though can cause bad visibility, and maybe we should consider a type of sensors such as radar. Yes, it will add cost, but consider the importance of the application. This wasn't really a competition. It all depends on the type of project and how many images we have available for a successful implementation, either in deep learning or traditional computer vision algorithms. Thank you.